Hello and welcome to Chemi at KPS, where chemical engineering meets clarity. I am Dr. Krishna Prasad Sadangi. On this channel, I break down the toughest problem in mass transfer into simple, step by step solutions rooted in fundamental principles. Whether you are preparing for exam or curious learner trying to master diffusion, absorption, distillation, then Chemi at KPS is your go-to guide. Here, you will find easy to follow walkthroughs of complex numericals, visual explanation of key concepts, a focus on understanding, not just memorizing, because I believe that every learner deserves clarity. My goal is to make chemical engineering accessible, logical, and every even enjoyable one problem at a time. So today we will learn the use of Chapman Enskog equation. So this Chapman Enskog equation is generally used to determine the of diffusivity through a stagnant non-diffusing layer. This is now in front of you. The Chapman Enskog equation for gas diffusivity is visible. Okay, so this is an empirical theoretical law derived from kinetic theory of gas and often called the Chapman Enskog relation for binary gas diffusion. This Chapman-Enskog equation is a theoretical formula that predicts the binary diffusivity of gases based on their molecular properties and temperature and pressure. It shows how fast molecules mix via diffusion in a gas phase. When the experimental data is unavailable and you need to determine the diffusivity, and if the molecular weight, temperature, pressure values are available, then this Chapman-Enskog equation is used to determine the diffusivity. Mainly, the key mass transfer problems associated with gas absorption, striping, diffusion through membrane, this predict the diffusivity. So now you see in front of you the equation is written. Okay. So in this equation you see temperature is mentioned over here, your molecular weight of one component is over here, then molecular weight of another component, then in the denominator you will find the pressure, you will find the collision diameter, the sigma, you will find this omega. Okay, so if all these values are known to you, then only you can calculate this DAB or the diffusivity. Okay, so now you see, if you assume that the sigma AB and your omega D, that is your collision integral, are constant over a small temperature range, then the relation comes into the picture that DAB is proportional to T to the power 3 by 2 divided by the P. Okay. At constant pressure, we can write right now that DAB is proportional to T to the power 3 by 2. Okay. You have to remember this equation. DAB is proportional to T to the power 3 by 2. Okay. So if one diffusivity is mentioned in the question at a particular temperature and you need to determine the diffusivity at another temperature. Another temperature means the operating temperature at which diffusion occurs. Then this relation helps you. Okay. So it says that DAB1 divided by DAB2. 1 and 2 means at position 1 at position 2. Okay. So is equals to T1 divided by T2 to the power 3 by 2. Okay. So now we can write DAB2 equals to DAB1 multiplied by T2 by T1 3 by 2. So if you have the temperature value, then you put it then you will get the diffusivity at position 2 and at that particular temperature. Okay. Now let's say pressure is not constant. Okay. If pressure is not constant, then we have to put the value of pressure over here, and the equation will be in this form, that dAB1 divided by dAB2 is equals to T1 to the power 3 by 2 by P1 divided by T2 to the power 3 by 2 by P2. Okay. Then you can put the values and you can determine the unknown one. Okay. So dAB2 can be determined by this way. Okay. So let's see the problem over here. What the problem says, that alcohol vapor is being absorbed from a mixture of alcohol vapor and water vapor by means of non-volatile solvent, in which alcohol is soluble but water is not soluble. The temperature is 97 degrees centigrade and the pressure is 760 mm Hg. That is 1 atmospheric pressure. The alcohol vapor can be considered to be diffusing from a film of alcohol water vapor mixture 0.1 mm thick, and the mole percent of alcohol in the vapor at the outside of the film is 80%, and that on the next inside the solvent is your 10%. The diffusivity of alcohol water vapor mixture at 25 degrees centigrade and 1 atmosphere pressure is mentioned over here, that is your 0.15 centimeter square per second. Now you need to calculate the rate of diffusion of alcohol vapor in kg per hour if the area of the film is given, that is your 10 meter square. The pictorial view is in front of you. Okay. Now you can see this is a box divided into three parts. Okay. The first left side part shows it contains alcohol water vapor mixture, and the right side one contains the non-volatile solvent. That means in this part only the solvent that is available, that is not soluble, or the water is not soluble in that solvent, but alcohol is soluble in that. And in the middle that you are getting over here, that is the film, and the film thickness is given, that is 0.1 mm thick, and the area that is given 10 meter square. Now this diffusion occurs at 97 degrees centigrade and 760 mm Hg, but the diffusivity is given in the question at 25 degrees centigrade. That means you need to calculate the diffusivity at 97 degrees centigrade. Okay, but you see the pressure is constant. Okay, in the question it is mentioned at 25 degree 1 atmosphere pressure, the diffusivity is mentioned 0.15 centimeter square per second, and also it is mentioned that it is total pressure is your 760 mm Hg. Okay, so pressure is constant over here. So at one temperature diffusivity is given, at another temperature at which the diffusion occurs you need to determine the DAB. Then we have to calculate the rate of diffusion, okay, in kg per hour. Now the solution is in front of you. This is a steady state diffusion problem involving a non-diffusing stagnant component. Okay, especially this kind of problems falls under the unidirectional steady state diffusion with stagnant non-diffusing B component in a binary system. Okay, so this is very important to understand what kind of problem it is. Understood? Now what is given? The film thickness is given, that is Z 0.1 mm, and the alcohol percentage is mentioned over here 0.8, that is your Ya, and 0.1, that is your this is Ya1 and Ya2. Okay, now the total pressure is mentioned over here 760 mm Hg, temperature is mentioned 97 degrees centigrade, and diffusivity is also mentioned over here. Now you see over here everything is given in meter square, so all the values should be in 1 unit. So it can be, the thickness can be 0.1 mm, can be 0.1 into 10 to the power minus 3 meter. Okay. So now the question is asked to calculate the rate of diffusion of alcohol vapor in kg per hour. Now we know that this Chapman Enskog equation says dAV is directly proportional to the temperature to the power 3 by 2. What it says? It says that the diffusion increases with increasing in temperature and the rate of diffusion decreases with increasing in the pressure. Okay. So now we can write dAV1 as per the previous slide that you understood that one temperature diffusivity is given at another temperature, that is the operating temperature, we need to calculate the diffusivity. That's why dAV1 divided by dAV2 is equals to T1 by T2 to the power 3 by 2. Now you see temperature is given everywhere, T1, T2, dAV1 also given, we need to calculate the dAV2. Okay, so we put the values over here and we will get the dAV value is equals to over here, that is 2.075 into 10 to the power minus 5 meter square per second. Okay, now what is our duty? Our duty is to calculate the rate of diffusion of alcohol in kg per hour. Okay, so Fick's law of non-diffusing stagnant component, Fick's law for non-diffusing stagnant component, we can write the flux over here that Na equals to dAB Pt by ZRT ln 1 minus Ya2 divided by 1 minus Ya1. Okay, so we can put all the values over here and we'll get the value, the flux equals to your 0.01029 kilomole per meter square second. Since it is given to calculate the rate of diffusion of alcohol vapor in kg per hour, so we can multiply it, the area in, that is 10 meters square, we can convert into the hour, we can multiply it that 3600 second per hour. Also we can assume that the alcohol present in that vapor, that is the ethanol, and we can use it, that is your 46 per kg mole, 46 kg per kilomole or gram per mole also you can assume it, and we can find out the rate of diffusion over here in kg per hour, that is 1.70 into 10 to the power minus 4 kg per hour. Okay, I hope you understood how this Chapman Enskog equation is being used to calculate or to predict the diffusivity at another temperature if diffusivity is given at one temperature. So if you like, then definitely you subscribe this channel, like this channel and share. Thank you so much. We'll see you in the next, again another video in another new topic. Thank you so much.